Have you ever felt that shiver down your spine? That unsettling sensation, as if something far more advanced than a camera, something almost impossibly sophisticated is watching you? Something quantum. The idea of a quantum computer tracking our every move sounds like science fiction, a concept ripped straight from the pages of a futuristic novel. A super-intelligent machine peering into our lives, analyzing our thoughts, and predicting our actions. But is there any truth to this fear? Is it a legitimate concern or simply a product of our overactive imaginations? Are these mysterious devices, shrouded in scientific jargon and complex equations, the ultimate surveillance tool? Before we get swept away by the hype and sensationalism, let's clarify something crucial. Quantum computers are not just faster, more powerful laptops. They're fundamentally different, operating on principles that seem almost magical, defying our everyday understanding of how the world works. This inherent strangeness fuels myths, anxieties, and a general sense of unease. When we don't understand something powerful, especially something so conceptually challenging, our imaginations fill in the blanks, often with worst-case scenarios. The fear of being watched, of being scrutinized and judged, is ancient, but projecting it onto new technology, without understanding its true capabilities, can lead to profound misunderstanding and unnecessary fear. The narrative of quantum computers as all-seeing eyes capable of penetrating our deepest secrets is largely a reflection of our digital age privacy concerns, amplified by the unknown, not a reflection of reality. So let's set aside fear, at least for now, and seek understanding through knowledge and exploration. We'll explore what quantum computers really are, demystifying the technology behind the headlines, how they work, delving into the core principles that govern their unique capabilities, and what they can do, examining the potential applications that could revolutionize industries, and, just as importantly, what they can't do, understanding the limitations that prevent them from becoming the all-powerful surveillance tools of our anxieties. By the end, you'll see that while quantum computers may very well change the world in profound ways, they're not the silent spies lurking in the shadows of our nightmares, poised to invade our privacy. The universe has handed us new tools of immense power and potential. It's up to us, as a society, to use them wisely, ethically, and responsibly. Let's face them with curiosity, with a thirst for knowledge, not with fear and unfounded suspicion. Welcome to the real story of quantum computing, a story far more fascinating and nuanced than the myths would have you believe. To understand the groundbreaking potential of quantum computers, let's first take a look at the classical computer, the very device you're likely using right now to watch this. Classical computers, at their core, rely on bits, simple on-off switches, representing information. These switches translate to ones and zeros. Every single digital action, from sending an email to streaming a video, boils down to long strings of these bits being processed. This binary system, while seemingly simple, has powered incredible feats, from mapping the complex human genome to connecting billions of people worldwide through the internet. But even the most powerful and fastest classical computers eventually hit a wall when faced with certain complex problems so intricate that they would take longer than the age of the entire universe to solve using conventional methods. This is where the quantum computer comes in, a machine which doesn't just play by a different set of rules, it completely reinvents the game itself. Instead of bits, quantum computers use quantum bits, or qubits. To understand this, imagine a light switch that has the ability to be on, off, and both on and off at the exact same time. A qubit can exist in a superposition of states, a concept that allows it to represent 0, 1, or a combination of both simultaneously, opening up a world of possibilities. This ability is the very source of quantum power, the ability to hold and manipulate multiple values all at once. The difference between classical and quantum computing isn't just about speed, it's about the sheer complexity of the problems that can be tackled. 2 classical bits can represent only one of 4 possible combinations at any given time. However, 2 qubits, thanks to superposition, can represent all 4 combinations simultaneously. With just 300 interconnected qubits, a quantum computer could potentially represent more values than there are estimated to be atoms in the observable universe. It's not just a minor step up in processing power. It's a quantum leap into an entirely new dimension of computation and problem solving. Quantum computers, in essence, mirror the complex probabilistic nature of reality itself, allowing for calculations that were previously impossible. They're not simply faster versions of what we already have, they're fundamentally different in how they process information. And that fundamental difference is precisely what makes them both so incredibly powerful and, for many, still so deeply misunderstood. So what is a qubit? It's not a tiny light switch. It's a quantum-scale particle, like an atom, ion, photon, or a superconducting circuit. The key is control. Scientists manipulate quantum properties like electron spin or atomic energy levels to represent 0 and 1. But the quantum world is fragile. The slightest disturbance, vibration, heat, or magnetic field can destroy a qubit's delicate state, a process called decoherence. To protect qubits, quantum computers are built in ultra-cold, isolated environments, massive refrigerators colder than deep space. Building a quantum computer is more like constructing a particle accelerator than assembling a PC. Every component is a feat of engineering, designed to shield the quantum core from the noisy outside world. We're not building surveillance devices. We're building scientific instruments that push the boundaries of what's possible. Quantum computers are grand experiments, not cosmic spies. Let's dive into superposition, the heart of quantum computing. In our world, things are definite. A coin is heads or tails. In the quantum world, particles can be both at once. A qubit is like a spinning coin, embodying both 0 and 1 until measured. This allows quantum computers to explore countless possibilities simultaneously. Classical computers check each outcome one by one. Quantum computers consider all at once. For certain problems, this is a game changer. Millions of simulations run in parallel, but this power is delicate. The moment you measure a qubit, the superposition collapses to a single outcome. Quantum algorithms manipulate probabilities so the right answer is most likely when measured. It's not a direct window into all possibilities, it's a dance of probabilities. The magic is in the process, not in peaking at every outcome. Superposition gives quantum computers their edge, but it's not a tool for surveillance. It's about exploring the unknown, not watching the known. That's the real art of quantum computing. The second pillar of quantum power, and perhaps the most intriguing, is entanglement. It's what Albert Einstein famously called spooky action at a distance, a term that captures the counterintuitive nature of this phenomenon. Entangled qubits are inextricably linked, sharing a bond that transcends physical space no matter how far apart they may be. Measure the state of one, and you instantly and simultaneously know the state of the other, regardless of the separation. In a quantum computer, entanglement creates powerful correlations between qubits, allowing these qubits to work together in ways that classical bits simply can't achieve, unlocking new computational possibilities. This unique collaboration enables complex calculations and supports the execution of famous algorithms, like Shor's algorithm, which is designed for factoring large numbers with remarkable efficiency. But it's important to remember that entanglement isn't magic. It doesn't violate the laws of physics. It doesn't let you send messages faster than the speed of light. It's not a tool for instantaneous communication or for spying across the vast expanse of the universe. The outcome of any individual measurement is fundamentally random. You can't predetermine or control it. Only after comparing the results through classical communication channels do you begin to see and understand the spooky connection. Entanglement is a valuable resource for quantum computation, enabling new algorithms and problem-solving approaches, not a tool for surveillance or intrusion. It's fundamentally about harnessing the deep and intricate connections that exist within nature, not about breaking or circumventing the established laws of physics. Quantum computers leverage entanglement to solve complex problems, not to infringe on privacy or to watch people's activities. The real wonder and excitement lies in the science itself, in the potential discoveries, not in the realm of science fiction. Entanglement is undoubtedly strange and perplexing, but it's not sinister or malicious in any way. It's the secret sauce, the key ingredient, that unlocks the true potential of quantum power. So, are quantum computers watching us? Absolutely not. Quantum computers are specialized calculators, not surveillance devices. They don't gather or process personal data. They solve specific complex problems. Classical computers, not quantum ones, are used for data mining and surveillance. Qubits are fragile. Any interaction with the outside world destroys their quantum state. The very act of watching would ruin a quantum calculation. The myth of quantum surveillance comes from misunderstanding quantum mechanics, confusing the observer effect with actual observation. In reality, quantum computers are focused inward, not outward. They're introverts, not spies. The real privacy risks come from classical technology and data policies, not quantum physics. Quantum computers are too busy solving mysteries of the universe to care about your emails. If quantum computers aren't spying, what are they for? Their true power is solving problems beyond classical reach. In medicine and material science, quantum computers could simulate molecules and reactions perfectly, revolutionizing drug discovery and material design. Imagine designing new medicines or superconductors, or creating catalysts to fight climate change. Quantum simulation could unlock breakthroughs we can't yet imagine. Another key area is optimization, finding the best solutions in logistics, finance, and AI. Quantum computers can explore vast solution spaces simultaneously, making them ideal for these challenges. And yes, cryptography quantum computers could break current encryption, but this is a known, manageable risk. Cryptographers are already developing quantum-resistant methods. The quantum revolution is about advancing science, not undermining privacy. These machines are tools for discovery, not surveillance. Their purpose is to expand human knowledge and capability. The real impact will be in labs and industries, not in your inbox. Quantum computers are here to solve, not to spy. Should you worry about a quantum computer reading your emails? No. Quantum computers aren't practical tools for personal surveillance. Their complexity and purpose are far removed from hacking your social media. The real threats to your privacy are insecure passwords, phishing, and data breaches, classical problems needing classical solutions. Even the long-term encryption threat is being managed. Upgrades will happen behind the scenes. For most people, the transition to quantum-safe security will be seamless. The quantum revolution will unfold in labs, not in your browser. Its impact will be indirect but profound. New medicines, better tech, deeper understanding. Embrace the wonder, not the fear. The quantum gaze is fixed on the mysteries of the universe, not on you. We're at the dawn of a new computational era. Today's quantum machines are primitive, but their potential is vast. Quantum computing isn't about replacing your laptop. It's about partnership. Classical and quantum computers will work together, each playing to their strengths. This is a global effort, with scientists and engineers worldwide pushing the boundaries. The breakthroughs will belong to all of humanity. The real story is one of curiosity and ingenuity, not fear. Quantum computers are like telescopes for reality itself, revealing what was once invisible. They won't be watching you. They'll be working for you, solving humanity's greatest challenges. The universe is whispering its secrets, and we're finally building a machine that can listen. That's the true wonder of quantum computing.